Hello, everybody. Thanks for being here. So I'm Stanislas Gaudry, and today I'm going to make the lecture about resistance and powering of a ship. So in the planning, we are here, so resistance and powering, and I will focus on the ship resistance. So while making a ship, we design first the hull, and we need to determine how much power we need to make the hull moving. So it's really important to know which resistance there is, to know which horsepower we need. So before, at the Roman Empire, there was only the wind power, so we were limited. We only use the power of the wind and also the people ramming. But since the 80s, we have now engine, like steamboat engine, and we are not limited by the power. We are more technologies. And now, for example, we use like a screw propeller. And so, for example, for a ship like cargo, we want the higher transportation efficiency. So we want big ship, and so the capacity of a cargo is proportional to length power free because it's a volume. But at the same time, the ship resistance is proportional to the surface. So the length, the power too. So will be limited by that. And I put some example of boats. So the Knot Nevis is the biggest boat that has existed. So do you know how big is it? What is the length of the biggest boat?
I would say around 400 meters.
Yes,
something like that.
It's a little bit more. So it's 458 for the biggest boat. The Knot Nevis. I put some other boat as to compare. And here is the map of Kaist. So we can see like a boat of 400 meters go from the one corner of the stadium to kind of like the library. So both are very big. And for information, for the Knot Nevis, the power of the boat was 37,300 kilowatts. So it's approximately 11 tons per horsepower. And so to predict the ship resistance, it's really complicated. It's not science, it's art. And so it's given mainly by testing. So it's empirical evidence from model and test of existing ship. And it's also influenced by sea condition and cargo loading condition. So it's really hard to determine because we can only see the real resistance on a real ship. And as the boats were very big, it's impossible to do like a prototype of it. So usually the final product would be the first prototype. Here I introduce you about some resistance. So there is the frictional resistance due to the boat. So the boat is in water, so there will be it will be in a viscous fluid, so it will be a frictional resistance. So while the boat is moving, it will make waves, so some energy will be lost by making the waves. The eddy resistance is due to some energy lost by the vortex at the end of the boat. And there will be air resistance due to the aerodynamic drag from the part above water. And as you can see in this graph, so when the speed of a boat is low, like the resistance force will mainly be due to the viscous resistance. But when the speed will increase, the energy loss will be due mainly by the wave made during the movement. And we can see that the air resistance is very little compared to the two others. So why we have resistance when the body is submerged? So this is a body submerged in an ideal flow. So when it's like this, we will have like a normal pressure around the surface. And so there will, on a body like this, there will be two components. One component will resist the motion when the fluid will go like this. This resists the motion. And this component will assist the motion. But since the flow is not ideal, there will be like some particle will kind of, let's say, stick to the boat. So the speed of the particle here will be like equal to the speed of the boat. So it will create like the boundary layer. So at the end, like we will have more pressure here. So only the component resisting the motion. So that's why we have a viscous resistance force. And on the real sheet, you can see here like some vortex created by the movement. So there will be energy loss here also. And if you have done fluid mechanics before, we'll see that there is two types of flow, laminar and turbulent. And so there is the Reynolds number, which can determine which type of flow we are. And the Reynolds number is the length of the boat times the velocity, the speed, divided by the kinematic viscosity of water. And while calculating this number, if the number is below 5 for like this number will be in a laminar flow. If it's above this number, will be in a turbulent flow. And there is like a transition from laminar to turbulent between those two. So on a sheet, we'll be in a laminar flow at the beginning of the boat, the hull, and then it will be turbulent on the side. And here we can see the vortex created. And so I put some numbers for the Noble Davis, the boat we saw before. And if you do the calculation, we'll see that we'll be on a turbulent flow. So a lot of loss energy. So as you can see, so there is loss due to viscous resistance. So the shape of the boat will have a huge impact. And so we can see like a shape like this has a lower coefficient of viscous resistance. So it's a shape like fish. So we can see that it's move easier in the water, and shape like flat plate or prism like this, where it's frontal to the water, will have a higher coefficient. So that's why boats are designed like this, like fish. And now I'll talk about the wave making resistance. So when a boat is, like when an object is moving on the water, it will create many waves, like a divergent wave. So there is a scientist Kelvin who studied that. And so like energy will be lost because because the wave are created. And I found on the internet like this curve that show like the total resistance coefficient on the speed left ratio. So that means like the wave created by the boat is like have an impact of the length of the wave is related to the speed of the boat, and the more the boat goes, the more the length, like the more the speed is high, the more the length also will be high. So it's kind of proportional. And there is some configuration, but to vote in a better way. So, for example, we can see that here there is a bump, it's decreased because like the vote will be in a position like it will be at the hollow of the wave. So that's a better situation that when the boat is at the crest of the wave. And there is a system to remove the impact of the wave, like it's called the bulbous ball. So there is this part at the bottom will create another wave, and so it will be this destructive interference. So the wave will be smaller. And we can see on the Eureka building, there's a model of a boat with this bulbous ball. And if you want, I can show you a little video about how the chip resistance is tested.
30년 넘게 의사 생활을 하면서 50이 넘었을 때 어느 날
Escape.
Escape?
Escape.
Oh, yeah. It's okay?
Yeah.
So you see there's the boat. They measure the April.
Break.
Yeah. Thank you for your attention.
No, we don't. All right. Any question, team?
Question? Was all clear?
All clear?
Perfect.
All right, then we can move on to discussion session.